By 2026, every AI agent in your Kubernetes cluster will speak the same language, or your entire system crashes.
Wait, are you saying our current multi-agent setups are ticking time bombs? So we're breaking down the new cloud-native standards, the security requirements, and how to migrate existing systems?
By minute 4, you'll know exactly which standards to implement first. Let's get into it.
Welcome to the Platform Engineering Playbook Daily Podcast. Today's news and a deep dive to help you stay ahead in platform engineering.
Today we're diving into cloud-native agentic standards.
Stick around to the end for today's headlines. Let's dive right in.
So let's talk about something that's becoming increasingly critical: cloud-native agentic standards. We're seeing this explosion of AI agents being deployed in Kubernetes environments, and it's starting to feel a lot like the early days of microservices all over again.
Wait, are we talking about AI agents that actually run autonomously in containers? Like making their own decisions about what to do next?
Exactly. These aren't just your typical microservices. We're talking about containerized applications that leverage AI or machine learning to reason through problems and execute actions based on signals from their environment. They can operate independently or collaborate with other agents to achieve consensus-based decisions.
That's wild. So we're essentially deploying AI systems that can plan, orchestrate, and govern their own execution within our Kubernetes clusters?
That's right. And here's where it gets interesting and concerning. Just like we saw with the early adoption of containers and microservices, we're facing a massive standardization gap. Different vendors are building these agentic systems in completely different ways, with no common framework for how they should communicate, how we should secure them, or even how we should observe what they're doing.
Oh man, I remember the chaos before we had standards for container networking and service mesh. Are we heading down that same path again?
It's actually worse in some ways. With traditional microservices, at least we understood the boundaries of what the service could do. It would receive a request, process it according to predetermined logic, and return a response. But with agentic systems, we're dealing with components that can reason through multi-hop problems and take actions we might not have explicitly programmed.
So what happens when you have multiple AI agents from different vendors trying to work together in the same cluster? That sounds like a recipe for disaster.
You're hitting on exactly why this standardization effort is so critical. Imagine you've got an agent from OpenAI, another from Anthropic, and maybe a custom one your team built, all trying to coordinate on a complex task. Without standards for how they communicate, authenticate, and share context, you're looking at integration nightmares that make early microservices look simple.
And I'm guessing the security implications are pretty severe too. If these agents can make autonomous decisions, how do we ensure they're not doing something harmful?
The security challenges are unprecedented. We need to think about not just traditional container security, like minimizing attack surfaces and enforcing least privilege, but also about AI-specific risks. What happens if an agent gets compromised and starts making malicious decisions? How do we implement guardrails that don't cripple the agent's ability to be useful?
This feels like we need a whole new set of Kubernetes primitives. Are the current abstractions even sufficient for this kind of workload?
That's the million-dollar question. The paper we're discussing today argues that we can build on existing Kubernetes foundations, but we need to extend them with agentic-specific considerations. They're proposing a framework that covers 4 key areas where standardization is desperately needed.
Okay, I need to hear about these 4 areas because right now it sounds like we're flying blind with these deployments.
Coming up, we'll dig into exactly what these standards look like and why each one is critical for scaling agentic AI safely in production environments. So the framework breaks down into 4 critical areas: general container best practices adapted for agents, security considerations specific to autonomous systems, observability requirements for understanding agent behavior, and availability patterns for fault-tolerant agent deployments.
Okay, let's start with the container best practices. How different are they from what we're already doing?
The fundamentals are similar, but the implications are amplified. Take the principle of least privilege, for example. With a traditional microservice, you might give it access to a database and maybe an API endpoint. But with an agentic system that can reason and take autonomous actions, every permission becomes a potential vector for unintended consequences.
So if I give an agent permission to scale deployments, it might decide to spin up 1,000 pods because it reasoned that would improve performance?
Exactly. And that's why the standards emphasize not just limiting permissions, but implementing what they call layered reasoning architectures with built-in controls. Think of it like guardrails that check the agent's decisions before they're executed. You might have one layer that validates resource requests against budget constraints, another that checks for security policy violations, and so on.
That makes sense. What about the observability side? I imagine debugging these systems is a nightmare.
It's not just about debugging, it's about understanding what the agent is thinking. Traditional observability gives us metrics, logs, and traces. But with agentic systems, we need what I call reasoning traces, a record of how the agent arrived at its decisions.
Can you give me a concrete example?
Sure. Let's say you have an agent managing database query optimization. Traditional observability would tell you that the agent modified an index at 3:47 p.m. and query performance increased by 23%. But reasoning traces would show you that the agent analyzed query patterns over the past week, identified that 78% of queries were filtering on a non-indexed column, calculated the potential performance gain versus index maintenance cost, and then decided to create the index.
That's incredibly powerful for understanding and trusting these systems, but I imagine storing all that reasoning data gets expensive fast.
You're absolutely right. The standards recommend a tiered approach. Critical decisions get full reasoning traces stored for compliance and debugging. Routine operations might only store summary reasoning or sampling. And there's a whole section on using observability data to train and improve the agents themselves.
What about the security angle? Earlier you mentioned AI-specific risks. What does that actually look like in practice?
This is where things get really interesting. Beyond traditional container security, we're dealing with prompt injection attacks, model poisoning, and what they call goal hijacking, where an attacker manipulates the agent's objectives. The standards propose a multi-layered security model that includes input validation specifically for AI contexts, runtime behavior monitoring that can detect when an agent starts acting outside its expected parameters, and isolation mechanisms that prevent compromised agents from affecting others.
So we're essentially building sandboxes within sandboxes. How does that work with the collaborative aspect you mentioned earlier?
Great question. The standards define secure communication protocols for agent-to-agent interaction. Think of it like service mesh for AI agents. You have encrypted channels, mutual authentication, and policy-based access control. But it goes further with things like semantic firewalls that validate not just the structure of messages, but their intent and potential impact.
That sounds computationally expensive. What's the performance overhead looking like in real deployments?
Early benchmarks from organizations implementing these patterns show about 15 to 20% overhead for full security and observability. But here's the thing, that's comparing apples to oranges. A properly secured and observable agentic system can actually outperform traditional architectures because the agents can optimize in ways static systems can't. We're seeing cases where agents identify and fix performance bottlenecks that human operators missed for months.
Okay, but what about when things go wrong? How do we handle fault tolerance for systems that might fail in ways we can't predict?
The standards address this with what they call graceful degradation patterns. Instead of traditional circuit breakers that just stop traffic, we have cognitive circuit breakers that can fall back to simpler reasoning models or even hand off to human operators. There's also the concept of agent consensus. Critical decisions require agreement from multiple agents, reducing the impact of any single agent failure or compromise.
This is fascinating, but I'm wondering about the practical implementation. Stick around. Jordan's about to break down exactly how to start implementing these standards in your own platform.
So let's get practical. If you're a platform engineer looking at this landscape, where do you actually start?
Yeah, because this all sounds great in theory, but I'm imagining trying to retrofit these standards into an existing Kubernetes deployment and feeling overwhelmed.
The good news is you don't have to boil the ocean. The framework suggests a phased approach. Phase 1 is establishing your foundation, implementing basic container security hardening for your AI workloads. This means using minimal base images, running as non-root users, and implementing resource limits. Nothing revolutionary, but critical groundwork.
So essentially making sure our container hygiene is solid before we add the complexity of autonomous agents.
Exactly. Phase 2 is where you start introducing Agentic-specific controls. Begin with a single, low-risk use case, maybe an agent that monitors and suggests optimizations, but doesn't automatically implement them. This lets you build out your observability pipeline for reasoning traces, without the risk of autonomous actions going wrong.
What would that observability stack look like? Are we talking about extending Prometheus and Grafana, or do we need entirely new tools?
It's a hybrid approach. You can extend your existing stack for basic metrics and logs, but you'll want to add specialized components for reasoning traces. OpenTelemetry is working on semantic conventions for AI workloads that include decision paths and confidence scores. Tools like Langfuse or Phoenix are emerging specifically for LLM observability, and they're starting to support the agent use case.
That's helpful. What about the security side? How do I start implementing these semantic firewalls without breaking everything?
Start with policy as code. Tools like Open Policy Agent can be extended to understand AI-specific contexts. You might begin with simple rules like agents can only modify resources with specific labels, or any action affecting more than X resources requires human approval. As you build confidence, you can add more sophisticated policies that examine the semantic content of agent decisions.
But won't that slow everything down? The whole point of autonomous agents is speed and scale.
It's about finding the right balance. The framework recommends categorizing agent actions by risk level. Low-risk actions like read operations or suggestions can flow freely. Medium-risk actions might require peer agent validation. High-risk actions need human approval or at least notification. Over time, as you build trust and refine your policies, you can shift more actions to lower-risk categories.
What about organizations that want to use multiple agent providers? How do we handle that interoperability challenge?
This is where adopting standards early pays dividends. The framework defines common interfaces for agent communication, similar to how we standardized on REST or gRPC for microservices. There's also work being done on agent adapters. Think of them like CNI plugins, but for agent communication. These translate between different agent protocols while maintaining security and observability.
So what should platform teams be doing right now to prepare for this future?
3 things. First, start experimenting with single agent deployments to understand the operational challenges. Second, contribute to the standardization efforts. The CNCF has working groups focused on AI workloads that need real-world input. And third, build your team's expertise in both cloud-native and AI technologies. The platform engineers who thrive in this new world will be the ones who can bridge both domains.
Any predictions on where this is heading?
I think we'll see Kubernetes operators specifically designed for agent workloads within the next year. We'll probably get CRDs for agent definitions, reasoning policies, and inter-agent communication rules. The service mesh providers are already working on agent-aware traffic management. And I wouldn't be surprised if we see agent-as-a-service offerings from the major cloud providers by the end of next year.
That's a lot of change coming fast. Any final advice for teams trying to stay ahead of this curve?
Don't wait for perfect standards before you start experimenting. The teams that are deploying agents today, even in limited ways, are learning valuable lessons that will inform those standards. But do it thoughtfully. Implement strong observability from day one. Start with low-risk use cases and always maintain human oversight until the patterns mature. Remember, we're not just deploying software anymore. We're deploying systems that can think and act. That requires a fundamental shift in how we approach platform engineering.
This has been incredibly insightful. The parallels to early microservices adoption really help frame where we're headed.
And just like microservices transformed how we build distributed systems, agentic AI is going to transform how those systems operate and evolve. The platform engineers who embrace these standards early will be the ones shaping this future. Before we wrap up, let's catch up on this week's infrastructure news.
The CNCF just welcomed 21 new silver members, and the focus areas really tell us where the industry is heading. Observability, AI, and secure cloud-native infrastructure are dominating the conversation.
It's interesting how observability has become table stakes now. Every platform team I talk to is drowning in metrics and logs, trying to make sense of their distributed systems.
Speaking of the CNCF, they just wrapped up the community awards at KubeCon Europe. These awards recognize the folks really pushing cloud native forward, the maintainers, mentors, and innovators who often work behind the scenes.
Those community awards are so important. It's not just about the big vendors, it's the individual contributors who make projects like Kubernetes and Prometheus what they are today.
Now here's where things get really interesting. The CNCF and Red Hat are making a major push to establish Kubernetes as the platform for distributed AI inference. They've introduced the LLMD framework and something called CARs, Kubernetes AI Requirements.
CARs? Another acronym. But seriously, this makes sense. If you're already running Kubernetes for your microservices, why spin up a separate infrastructure for AI workloads?
Istio is also jumping on the AI bandwagon with their latest release. They've got ambient multi-cluster in beta, plus a new gateway API inference extension specifically designed for AI workloads.
The ambient mode is huge for reducing resource overhead. No more sidecar proxies eating up memory in every pod.
AWS just reached GA with their load balancer controller support for the Kubernetes Gateway API. This replaces all those messy annotations with proper CRDs.
Finally, annotations were such a hack. Having real CRDs means better validation, easier automation, and cross-namespace routing that actually makes sense.
Let's talk releases. We've got some critical security updates. NATS Server dropped 2 security releases, versions 2.11.15 and 2.12.6. These fix multiple CVEs affecting MQTT and leaf node configurations.
If you're running NATS with MQTT or leaf nodes, update immediately. These aren't patches you want to delay.
Argo CD version 3.11.13 is also a security release. All their container images are co-signed and meet SLSA Level 3, which is becoming the gold standard for supply chain security.
SLSA Level 3 is no joke. That's build provenance, isolated builds, the whole 9 yards.
Finally, Pulumi 3.228.0 brings some nice quality of life improvements. They're not applying the secrets filter to Boolean values anymore, added gRPC secure support to their OTLP exporter, and they're reading OTEL resource attributes now.
The OTEL integration is key. More tools need to play nicely with the OTEL ecosystem. It's becoming the standard for observability data.
That wraps up today's news. That's our show for today.
If you found this valuable, please subscribe and share with a friend who'd appreciate it.
Drop us a comment with your thoughts on today's topic.
Links to everything we discussed are in the show notes.
And check out platformengineeringplaybook.com for more resources and guides. Until next time.